In this video, we're going to be looking at friction, which is an interesting kind of force because it behaves differently than things we've looked at before. So we're going to analyze situations where objects slide or try to slide relative to each other for the purpose of applying Newton's laws and doing Newton's laws problems with the frictional force. Friction gets a lowercase f rather than a capital F to differentiate it from all the other forces. It usually gets a subscript, a K for sliding, skidding friction, which we call kinetic friction, and an S for static friction. So we need to differentiate between static and kinetic friction. If something is at rest sitting on a ramp, you might look at this free body diagram and say it should slide down that ramp. Well, if there's friction, the static friction is what is keeping it from sliding down the ramp. If it is sliding down the ramp, well, there still can be friction if it is a rough surface, and that would be kinetic friction once it starts moving down the ramp. If we have something simply sliding across a board, if we're pulling it, giving it an applied force, and there is friction, then the friction would be kinetic. If it is not sliding, but we're giving it a pull, that would be notice that the board is being pulled and the object is moving with it, not sliding off, then it has static friction. This is not because the block is at rest relative to the ground, it's because it is not sliding or it is at rest relative to the surface it is on, right? Static and kinetic aren't about movement, they're about relative movement. So a couple of other scenarios that are worth thinking about. If you have a car wheel or a bike wheel or any wheel on the road skidding to a stop, you lock up the wheel and you go squeak and you slide. That would be kinetic friction because we have a tire sliding relative to the surface. If you're spinning your wheels trying to get going, right, on ice or sand or something like that, that's kinetic friction again, it's sliding, but the wheel is trying to spin backwards and the kinetic friction is trying to push you forwards. And the final scenario is when you are not sliding, not skidding on a normal roadway, there is actually static friction pushing you forward because the tire wants to slide backwards, but the static friction is pushing it forwards. So this gripping of the pavement is really what we're thinking about here, prevents relative motion. The static friction is preventing the tire from slipping relative to the ground. And so as we're thinking about this, we can think about it in terms of the third law. The car tire pushes backward on the road, which is a static frictional force, and the road pushes forward on the car. Another interesting scenario with this is if it's rolling forward at constant velocity, there's no need for static or kinetic friction, which is sort of counterintuitive because we can't really imagine this scenario. But if it is truly doing that, then there is no need for either. So there's a couple of things we should know about forces, the force of friction specifically. When it comes to direction, it always acts between two surfaces. Its direction is parallel to the surfaces as they try to slide relative to each other. And it always points as to prevent or reduce relative motion. It's always a good question to ask yourself, what would happen if there were no friction? And then think about, okay, what is the friction doing? When it comes to friction, we need to figure out what actually determines the magnitude, how big that force of friction is. There's lots of things you might imagine that friction depends on speed, area, weight, the materials, etc. It turns out there are only two things we care about for these types of friction: the surface materials, what the two objects are made out of, and the force pressing them together, which we call the normal force. So I'm going to do a little demonstration here, and hopefully this will help us understand what's going on. So I have here a graph of force versus time. I'm going to start with this one. This is just a block being pulled across a paper-covered board. So I'm going to get rid of that video for a second. And what we have is we have some amount of force that's growing, then it falls down. And this is the force of that particular block on a board. So that's what it is. It's a force. Now, I have a lot of other data here that I've collected as I pulled them. And one of the things that I did is I said, oh, well, let me stack another mass on top of that block. And that's this red line. Notice the maximum friction and the frictional forces are all bigger until I sort of let go. And as I keep adding 2, 3, 4 kilograms on top, we see that we keep growing in friction. So the more we're pressing the block down by stacking more mass on top of it, the bigger the frictional force. But that might make you think, well, isn't this really just talking about the mass? But it turns out that it doesn't have to be that. This is a scenario where the blue line is not more mass on top of it. It's me just pushing down on the block while it's being pulled. So I'm using an applied force to make it so that the normal force between them gets bigger. So that's the first piece, that when we're talking about this, friction depends on the normal force, right? And the normal force could be by stacking other things on top or by applying additional forces. All right. Now, the other thing that friction, we said, depends on is the material itself. So this is our starting one of just the block on the board with the piece of paper on it. And then if I pull the block along a different board, right, just on the paper, on the board itself, and then finally, I have one where I'm pulling it along our lab tables. Notice that all of these have slightly different forces that they apply. And really, we're kind of looking here in the middle as it's moving. There's something interesting going on as it gets started, but we have slightly different values of force for each set of materials. So that's the other thing, that the force depends on the materials involved. Now, the mechanism of friction kind of helps us understand all of this. There's this concept called cold welding. It's a molecular interaction, and then there's a force required to break these connections between the various materials. It depends on the normal force, right? This is another example. This is basically what I did. I applied more mass on the top, which made the normal force between them bigger. But you can also see that it doesn't really matter how fast you're going. If you're going really fast, the friction decreases a little bit, but we generally say that the kinetic friction is constant whenever it's moving. It doesn't depend on surface area either. This is a harder one to see, but it turns out that whether you take these two masses and drag them with a scale, either when they're stacked on top of each other or connected in the middle by a string, you get the same result. The basic idea here is that, yes, you have twice the surface area, but each mass then has half the normal force, is one way to think about that. So when it comes to kinetic friction, we can calculate it using a coefficient, or we can calculate a coefficient based on the kinetic frictional force. If we know how sticky the materials are, we get something we call mu k. That's a micro prefix symbol. It's a mu in the Greek alphabet for kinetic, and then the normal force is there. By definition, mu is the ratio of how much frictional force you get for every Newton of normal force. It is a unitless quantity or dimensionless because it is a ratio of two forces. There's a lot of things we can look at here. These are just typical values of coefficients of static and kinetic friction. But if you look carefully at this list, you will notice that the static frictional coefficient is generally bigger, or in cases where they're small, the same as the coefficient of kinetic friction, which means that the friction that holds things still relative to each other is stronger than the friction that slows things down once they're moving. So I want to demonstrate this as well. Static friction varies up to some maximum value and then drops off. So if I go back to my graph that we were looking at earlier, and this time I'm going to bring back our video. This is a video of me dragging the block across a surface. Specifically, it's this one I've called static and kinetic. We can take a look at a replay of what happens when we drag this block. So we can watch this. I'm pulling on it and it's getting stronger, then it breaks free, and I get a relatively constant force as I'm pulling it along. And so there's kind of three regions here that are worth looking at. There's this initial section where it's getting bigger and bigger, a static frictional force. Then there's this point where we are at our maximum static frictional force. And then we have a region here where it's a relatively constant. This one in the back is where I was pulling it at the closest to a constant velocity. So it bears looking at, what does all this mean? In a more idealized situation, you would get something like this. Frictional force grows and grows and grows as you're trying to pull it, but the frictional force is still big enough to stop it. Then we reach a maximum static value, we drop, and then we get into an approximately constant kinetic frictional mode where it moves along. And so that's the demo. So this is the graph that I just did. We have the growing static friction, we have the maximum static friction where the block breaks free, and then we have this sort of constant kinetic friction region. So when it comes to static friction, the way we calculate it is a little bit different. We can calculate using a coefficient, but this does not give us the static friction at all times. It just gives us the maximum value. And the maximum value of static friction, right, could be way bigger than what we need, or it could be less than what we need. And that's what we're going to play around with when we solve these problems. So these two formulas are empirical. That means we have to figure out what happens. We have to actually measure these forces. They're approximate. This is not, a purely theoretical thing like Newton's second law, where if you know the masses and you know the net force, you can predict an acceleration. This is a little bit more complicated than that. But it turns out you don't always even need the formula. If you're pulling something at constant velocity, you know that the forces have to be balanced. So if you pull with a force probe, which is what I did, or a spring scale to make those videos, the force you're measuring when you're pulling at constant velocity, or you're pulling it and it's not moving, is equal to the frictional force. So in this case, kinetic friction is 5 newtons. If it's at rest on a ramp, well, you can do the calculation for all the forces, and the static friction must be equal to the x component of the force of gravity. And if you keep lifting this board and you let that FGX get bigger and bigger, you can actually figure out what the static frictional force is when it finally breaks away, or the maximum value. So let's do an example here. A 1,000-kilogram car accelerates up a ramp. It's an 8-degree ramp at 3 meters per second squared. First of all, what kind of friction? Well, if it's accelerating up the ramp properly, it's static friction because the wheels are turning but not slipping. What do all the forces look like? Well, they look like this: normal force, force of gravity. If friction is the thing that's accelerating it up the ramp, then it must be in that direction, right? We can calculate the net force in the x direction. Net force equals ma. And then we can figure out that the static friction is in the positive direction and FGX is in the negative. We can solve for static frictional force, and we end up with about 4,400 newtons. Notice that I didn't use a coefficient of friction because we are not necessarily at Fs max. So imagine, if you will, that you're lost in the forest with a block, a plank, and a ruler, and you need to know the mu-s between your block and your plank. I don't know why. But you don't have a force gauge. What could you do? Well, I kind of gave it away earlier, but if you keep lifting up the plank to increasing angles and are able to measure the dimensions here, when it first begins to slide, you have just past Fs max. And so you can, fiddle around with it a little bit until you find the angle at which it releases and say, that's when Fs max was just overcome. And we can figure out the force of gravity in the y and the x directions. We can say that the FGX is equal to Fs max because the net force in the x is 0. It turns out that FGX is mg sine of theta. In the y direction, FGY is mg cosine theta, and that is the normal force. The ratio of static friction to normal force is mu-s. We can simplify this equation, and essentially, static frictional coefficient can be found by lifting up a board until the block just slips and taking the tangent of angle theta, which you might know simply by measuring the height and length of the triangle formed by the board. So mu-s equals tan theta max. You lift it up until you reach that point. We end up with a really interesting result, is that the maximum static frictional force that you might think makes sense is 1, where you get the same amount of normal force as you do static frictional force. But you can actually have some materials that are so sticky that you actually have a static frictional coefficient bigger than 1. Unusual, but it is possible. All right, so the big idea with all of this is that friction depends on the normal force and the materials involved. Friction is something we have to kind of figure out experimentally. It's not something we can do purely out of theory.